Section 5 deals with what we call implicit differentiation. So up until now, when you've taken derivatives for functions that have been written explicitly. Functions that are written implicitly require implicit differentiation. So I guess technically you could say you've been doing explicit differentiation so far. Explicit form means that it's like solved for y, or you have f of x equals, okay? So all three of these equations here are written in explicit form. And all three of these you can take the derivative of very easily right now. These equations here are also, for the most part, solved for y. But what's different? Yeah, there's other y's involved. So there's more than just x variables going on here. When that's the case, like right here, that guy or that guy, we're taking the derivative, but that's a y, not an x. That case, also implicit. In there we have that sine xy. That is not sine x times y. That is sine of xy. All three of these cases involve implicit differentiation if you're going to take the derivative. None of these are functions. Well, I'll take that back. This one here actually is a function. But this one is not, this one is not. So you're going to have graphs that are circles or other kind of cool looking graphs. And we can now, once we learn implicit differentiation, talk about tangent lines to those things as well. Because previously, we could only do that if it was a function. All right, to differentiate implicitly, we need the chain rule. So this is the chain rule once again, and we're using the dy over dx notation again. We're not using u and u prime and stuff like that. So we're jumping back into this. Dy over dx, I can split that into dy divided by 1 times 1 divided by dx again, and then that gives me room to make that du in between. We're using the same idea for implicit differentiation. So the notation that we're using is critical to how to understand how to do implicit differentiation. The other piece of notation we need is this guy right here. What does that say? The derivative, good? Good, there it is. The derivative, I just lost what I'm doing. Derivative of f of x with respect to x. Okay? If I had some other function, some other variable, and I wanted to take the derivative of that function with that variable, then I would say the derivative of my function with respect to whatever that other variable is. All right? It doesn't have to be x. In this case, though, it is. All right, so putting that stuff together, here's what the chain rule allows us to do so that we can actually differentiate implicitly. If the variable you're taking the derivative of disagrees with the variable in the equation, then you need to use implicit differentiation. So if I'm taking the derivative with respect to x, but I've encountered a y, those variables don't agree. So I have to use implicit differentiation there, which means I need the chain rule. So if I'm taking the derivative with respect to x of something, that's kind of like saying the derivative over 1 times 1 over with respect to x. This isn't the best math here, but it's the best way to explain how this works. So now I have this fancy 1 sitting here. I can put whatever I want there. I'm going to put a dy there. So now what I have, I started off taking the derivative with respect to x of something involving y. I can't do that because the variables don't agree. So I use the chain rule here, and now instead of the fancy 1, I'm going to put a dy over dy. So what it does for me now is it says, okay, now I can take the derivative with respect to y, but once I've done that, I have to multiply on the derivative with respect to x. And that is just going to be dy over dx. And that's it. Okay, there's nothing more to do there. But we have to make that math happen so that we can make our variables agree. So in other words, if I have the derivative of a function and I'm taking the derivative with respect to x, what winds up happening is you can take the derivative of the function with respect to y like you normally would, But when you're done, you have to tack on a dy over dx, and then you're done. Then, if you're looking for dy over dx, like if they say find dy over dx, find y prime, then solve for y prime. So here, we would divide both sides by whatever this is right here, and we'd wind up with dy over dx equals some probably rational function. And you'll see how that works here in a second. The last thing I want to say about this is if my function is written in terms of y, so y equals some stuff, I take the derivative of y, what do I get? We write y prime. We've been writing y prime, right? So I have this function here, and then I take the derivative and I have this function. But the real notation for y prime is dy over dx equals. Okay? So we are doing exactly the same thing here. We're winding up with that dy over dx, y prime, but we're writing it as dy over dx now. And there's a very good reason why we're going to do that. You probably won't realize that until the last section of the chapter. All right. So 3 examples here. The first example is you're taking the derivative with respect to x of x to the third power. In other words, the variables here agree, they match. Can I take that derivative normally? Yeah. So we take the derivative normally, the 3 comes down, x to the second power, so I have 3x squared. No problem. For the second one, I'm taking the derivative with respect to x of y to the third. Do my variables agree there? No, they don't. So that means I need to differentiate implicitly, okay? To do that, I need to rewrite this as, remember that the chain rule applies here, d over dy times dy over dx. So I can rewrite this as the derivative with respect to y of y to the third times dy over dx. Once I've done that, now I can take the derivative of this thing with respect to y, which is what? 3y squared. And then I got to multiply on the dy over dx, and that's it. What? We don't. You add it on to the end because you had to use the chain rule in order for you to be allowed to do what it's asking you to do. Okay? In this case, we don't know what that is. This isn't an equation we can solve. Normally, if we came up with this answer, then we would solve for dy over dx. And you'll see how that works once we get through these couple examples. Okay, the last one, d over dx. So the derivative with respect to x of x plus 3y. Can I do this? So the answer is yes and no here because we have 2 terms. The first term is a term with respect to x, so we can take the derivative normally there, but the second term is not. So I'm just using my very formal notation here. I can split up 2 functions being added and rewrite this as d over dx of x plus d over dx, the derivative with respect to x of 3y. Okay? I haven't done anything new there. I'm just writing this as 2 separate derivatives. Can I take the derivative with respect to x of this guy? Yeah, it's what? It's 1. Can I take the derivative with respect to x of this guy? No. So what will it become? Yes, 3 dy over dx. That's right. So plus, I'm going to rewrite this as d over dy, the derivative with respect to y of 3y times dy over dx. Now can I take the derivative of that? Yes. This is still 1 plus the derivative with respect to y of 3y is just 3 times the dy over dx. And you're done. There's nothing more we can do. Again, if this is a function, then we could solve for dy over dx, and we will be doing that shortly. All right, take the derivative with respect to x of xy squared. First of all, I'm not going to say anything else. What do you see? So what are we going to have to use? Going to have to use the product rule. That's right. Good job. Okay, so that means that what's f? And then g is the y squared. Okay? All right, now take the derivative. What do we have? So f prime will be, I'm taking the derivative with respect to x, remember. So I'm going to write this very formally. So it's going to be the derivative with respect to x of x times the original g plus g prime. So the derivative with respect to x of y squared times the original f. You guys are going to get to a point where you don't have to do this, hopefully very quickly. You can skip this very formal step here. So for the first term, derivative with respect to x of x, can I do that? Yeah, and I get 1, so just y squared. Plus, the derivative with respect to x of y squared, can I do that? No. What do I get? dy over dx, yeah. So think of it this way. I can just take the derivative of anything I want, but if the variable doesn't agree, then I tack on a dy over dx, or a d whatever over what it is that I'm taking the derivative of. Yes. So I'm going to take the derivative of this right now. It'll become 2y dy over dx, to complete the chain rule, times x. So it's y squared plus 2xy dy over dx. All right, so here's your summary for important tips. Safety tips for implicit differentiation that you need to be followed always, or you will crash and burn. Take the derivative of both sides of the equation, probably very importantly, with respect to x. Then you'll handle the implicit differentiation as you go. So once you've taken the derivative of both sides, you're going to have some dy over dx's hanging out. You want to collect all your terms with the dy over dx to the left side of the equation. I suppose you could move it to the right side of the equation if the situation made sense to do that. But basically, you want to get all the dy over dx's on one side of the equation. All those terms that have that in it on one side. All the other terms on the other side. So in this case, on the right side. Then factor out the dy over dx from all those terms on the left side. That will be a GCF that you can factor out.
Every single time?
Every time, because you've collected all the dy over dx terms on one side. So automatically you have a dy over dx that you can then factor out of all those terms. Then just solve for dy over dx by dividing both sides by the what's left over. Once you factor out the dy over dx, the stuff left over, that's the factor that I'm talking about here. Divide both sides by that factor, and now you've solved for dy over dx. It's a fairly straightforward process, but these are the steps on how to do it. Once you see how it's done, it should be not that tough, hopefully. All right, so all I have, that's the actual teaching of the section. So all we have now is a bunch of examples. Yeah. So here we go. Find dy over dx, given that y cubed plus y squared minus 5y minus x squared equals negative 4. Okay, so this is not a function. We cannot solve this for y. So that means we need to differentiate implicitly. Okay, now I've given you a fairly straightforward example here. There is no product or quotient rule or chain rule involved. Well, there is chain rule because you're differentiating implicitly, but there's nothing really major going on here. So we can take the derivative pretty straightforwardly. Can I take the derivative with respect to x of y to the third? No, so I'm going to instead take the derivative with respect to y and then tack on a dy over dx. So the derivative here will be 3y squared times dy over dx. Next term. Can't take the derivative with respect to x of y squared, but I can take the derivative with respect to y of y squared times dy over dx. So what do I get? Plus 2y dy over dx. Next? Minus 5 dy over dx. This one we can do normally, so we get minus 2x. We have to take the derivative with respect to x of both sides. So it's d over dx of that side, and it's also d over dx of that side. What do we get? 0. You have to do both sides of the equation. Just like if you add 2x to both sides of the equation, you still have to take the derivative of both sides of the equation, okay? And we actually have been doing that. Off to the side here, if I have y equals 2x plus 3 and I take the derivative with respect to x of both sides of the equation, take the derivative of y, what do you get? You get 1 times dy over dx, okay? You actually have been doing this the whole time, we just never talked about it. D over dx of y is 1 times dy over dx, which is y prime. So you have been taking the derivative of both sides of the equation every time. You just didn't know that, okay? So now we've taken the derivative with respect to x of both sides of the equation. The next thing we have to do is collect all of the dy over dx terms on one side, get all of the other terms on the other side. So since I have all my dy over dx's already on the left side, I'm just going to add 2x to both sides. And now I have 3y squared dy over dx plus 2y dy over dx minus 5 dy over dx equals positive 2x. Factor out the dy over dx. So dy, as we go on, we'll probably skip a couple steps here, but I'm just doing everything written out here. dy over dx is factored out times what's left over. Left over from this term would be the 3y squared. Left over from this term would be the plus 2y. And left over from this term would be the minus 5 equals 2x. Now divide both sides by this guy right here. 3y squared plus 2y minus 5. 3y squared plus 2y minus 5. That leaves me with the dy over dx here, because these guys go away. And I just have dy over dx equals whatever I wound up with over here. 2x divided by 3y squared plus 2y minus 5. And you're done. Determine the slope of the tangent line to the graph of. This is directions that we've seen before, okay? So nothing new there. You just now have to apply what we've learned to that, because I'm giving you the equation of an ellipse. So determine the slope of the tangent line to the graph of that. At the point, there should be parentheses, root 2, comma, negative 1/2. So let's take a look at the graph first. You can see that it's an ellipse. We have the square root of 2, so that's like 1.4, something like that, comma, negative 1/2. So we are talking about maybe that ordered pair right in there somewhere. Okay? So my answer for my slope should be what sign? Should be positive, because my tangent line will look something like this. Okay? So that's a positive slope, and maybe around 1, I don't know. Certainly not really steep though, so not 5. Okay? So do some sort of graphical analysis if you can. By the way, your calculators will write equations, or will graph equations in that form. You just got to learn how to do it. All right, so let's not worry about that right now. Let's worry about finding the slope of the tangent line. So that means I need to do what to that function? Take the derivative. All right, so let's take the derivative. All right, we're taking the derivative of the whole thing with respect to x. Take the derivative of the left side with respect to x. Take the derivative of the right side with respect to x. Derivative of the left side will be what? 2x plus 8y dy over dx, had to implicitly differentiate there, equals 0. Now what? So move the 2x over, and now I have 8y dy over dx equals negative 2x. Now what? Divide by 8y to get the dy over dx by itself. So dy over dx equals negative 1/4 x. So negative 1/4 x over y would become negative x over 4y. Right? Okay. That's the derivative. That's the same as writing y prime equals negative x over 4y. Okay? Now what? Yeah, so this time, like previously, we were just able to plug in the x coordinate, but now we are plugging in the entire ordered pair because we have x's and y's in this derivative. So I don't have any notation here to write down what I'm doing, so I'm just going to substitute in. I have a negative. My x coordinate is the square root of 2 over my y coordinate, which is negative 1 over the square root of 2. Well, and the negatives are gone, right? A negative divided by a negative is positive. Leave it, change it, flip it on this. Sorry, I forgot about the 4. So it's 4 times that. So leave it, change it, flip it on that, and we get, let me write that out so we don't get lost. The square root of 2 over 1 times, this is actually 4 over the square root of 2, so times the square root of 2 over 4. So that becomes 2 over 4, which is 1/2. We did get a positive slope. It isn't steep. It's very shallow, actually, and it does seem like my tangent line could have a slope of 1/2 here. So there you go. All right, that's how you do these problems. It didn't say give me an equation. It just said find the slope, so I did. Okay, so same type of problem. Determine the slope of the graph of that with this cool-looking graph at the ordered pair 3, 1. So we take a look at the ordered pair 3, 1. Here's 3, and 1 looks like it's right about there. So I might be right about there, and then my slope looks like maybe, I don't know, 1, 2, somewhere in that region, right? But definitely positive and not super steep. So now at least I have an idea of what my answer should look like. So we're ready to take the derivative. How do we do that? Well, let me back off a little bit here. We need to take the derivative of both sides with respect to x. So I'm just going to rewrite this so that we see it one more time, and then I probably won't do this ever again. The derivative with respect to x of 3 times x squared plus y squared, quantity squared, on the left, equals the derivative with respect to x of 100 xy on the right. Okay, look at the left side. Now step back from the situation and realize what this thing is asking you to do. How do I take the derivative of the left side? General power rule. Yeah, it's the chain rule, but more specifically general power rule. So let's do that. Now as we do it, inside, when we take the derivative of what's inside, we will have to use implicit differentiation for part of it, okay? So now you have an idea of where you're going. So take the derivative. The 2 comes down. 2 times 3 is 6. Times what was inside. So x squared plus y squared, that stays the same. Hold on. Decay the exponent by 1 becomes to the first power. All right, don't forget that. Now, what? Times the derivative of what's inside. So remember, we're taking the derivative with respect to x. So 2x. Good. Had to use implicit differentiation there. Is that it? Close the parentheses. Are we done? We're using the general power rule for this. The 2 came down. We rewrote what was inside. We decayed the exponent by 1. And then we had to differentiate implicitly on the inside. Good. Now move to the other side. Now step back again. How do I take this derivative? This is a product rule situation. You could apply the 100 to the x. You can apply the 100 to the y. You can pull the 100 out and treat it separately if you want to. However you want to do it. Personally for me, I'm just going to put the 100 on the x and call it good. So product rule here gives me what? 100y plus. Okay, so this is now g prime. G prime with respect to x will become 1 dy over dx. So dy over dx times the original g, which is, sorry, the original f, which is 100x. So times 100x. All right, are we done? I mean, are we done with the derivative? Yeah, we're done with the derivative. So what's our next move then? Like, what's our next goal? Right. So here's the issue. If we're trying to get all the dy over dx's on one side, this one's easy to get over there. But look at all this other junk that's tacked on to this guy right here. What should we do? Yeah, that doesn't work. So you sent the 6 in here? Okay. And then you foiled? If I divide right now, then that is going to make a really bad situation over here.
Minus 100y.
So you want to get this guy moved over here?
Yeah.
Why? If I'm trying to move all my dy over dx's over here, then this guy needs to stay put.
Minus dy over dx times 100x. And then divide by the factor.
That's going to get ugly. Ugly. You do want to distribute here, but not the way that you're used to. So just off to the side here, I'm going to change colors and I'm going to erase this here in a minute. If I have 3 times x plus y, I can distribute that, right? Okay. I get 3x plus 3y, right? What if I have a times x plus y? I can still distribute that, right? And I wind up with ax plus ay, right? But what if I came down here and I said a is actually equal to x squared plus 2? So that would give me x squared plus 2 here times x, right? Plus x squared plus 2 here times y, right? But what if I substituted that x squared plus 2 in up here to begin with? Now I'd have x squared plus 2 here, then times the x plus y here, right? But can't I take this thing as one whole thing here and distribute it to that, and then again do that to that? And does that not give me that result right there? Okay, so we are not going to FOIL. We are going to distribute this right here as one whole thing to this term and also to this term.
Okay, so I wasn't quite right.
You weren't quite wrong either.
No.
You were the closest. But that's what we're going to do. So let me get rid of this just so that you see how that works. Okay, so this whole thing right here needs to get distributed to that and to that. So what do I write?
So 6 times 2x.
So the 6 times 2x becomes 12x. Times.
X squared plus y squared.
Good? Okay. Now we're distributing this to here, and that becomes
12y dy.
12y, x squared plus y squared, dy over dx. Now look what happened. We're done on that side, and now we can get the dy over dx term by itself. Okay? If you had FOILed, you would have created all sorts of dy over dx terms, and the ugliness would have continued. But now this is actually kind of relaxing to me. I feel good right now. On this side, do we need to do anything special? No, not really. So I'm just going to rewrite it. 100y plus 100x dy over dx. Okay. dy over dx on the which side? Left? All right. So that makes 12y parentheses x squared plus y squared dy over dx. I'm moving this guy over, so minus 100x dy over dx equals 100y minus 12x x squared plus y squared. I factor out the dy over dx.
Please report to the office.
Parentheses 12y minus 100x equals 100y minus 12x parentheses x squared plus y squared. Divide both sides by the 12y minus 100x and I have dy over dx equals 100y minus 12x parentheses x squared plus y squared over 12y minus 100x. Then we plug in that ordered pair. 3 for x, 1 for y. Simplify it down. And you'll have the slope of your tangent line at that ordered pair. Okay? And I'm sure you can handle that.